Yes, in today's class, we are going to talk about the instruction set architecture. So, what is instruction set architecture? So, the basic introduction we can say that to command a computer's hardware, you must speak its language only because computer don't understand the high level language as we discussed in previous lectures. It understands only the machine level language. So that's why we say that you must speak in its language only. So the word of a computer's language are called instructions, and its vocabulary is called an instruction set. So you will see the instruction set of a real computer, both in the form written by the people and in the form read by the computer. So we introduce instructions in a top-down fashion starting from a notation that looks like a restricted programming language. Then we refine it step by step until you see the real language of a real computer. So you might think that the language of computers would be as diverse as those of the people, but in reality, computer language are quite similar, more like the regional dialects than like independent languages. So hence, once you learn one language, it is easy to pick up others too. So the chosen instruction set comes from the technology we call MIPS technology. We call MIPS technology. So this MIPS technology, M stands for millions of instructions per second technology. Based on that, we are going to talk about this millions of technology instructions, and it is and the elegant example of the instruction set design since the 1980s. So to demonstrate how easy it is to pick up other instruction sets, we will take a quick look at different popular instruction sets in the upcoming the slides. But for this instruction set architecture, the topic, we are going to follow the two books, the optional reading books. One is Computer Organization and Design, that covers this chapter covers from the chapter 2, that is instruction, that is language of computer, and from the second book, Computer Architecture, the quantitative approach. From there, we follow the Appendix A, which gives the instruction set principles for reading purpose of this instruction set architecture. So in this instruction set architecture, what we are going to talk about, we are going to talk about the basics of instruction set architecture, the standard structure of your instruction set. And then we talk about the ISA design choice and the classification. So we basically discuss about the classification of ISA, and after that we try to design those the instruction set architecture in terms of hardware by following the AND gates, as we and some the OR gates, and some the NOT gates. So that is the design choice, and based on the ISA, we are going to classify the instruction sets into two different parts. One is CISC, another one is the RISC. CISC is the complex instruction set computer, whereas RISC is reduced instruction set computer. We are going to talk about this in detail later. And after that, how we are going to implement these instruction set architectures on the hardware part by using the arithmetic and logical unit, the hardware part, based on how we are going to implement that we discuss. And then we cover the another specific technology called the SIMD instruction set technology, that is single instruction multiple data, and finally how these instructions are converted from the assembly language to the low level language or machine level language with the help of your computer compiler that we are going to talk in this. So comes to, if you observe in this roadmap, the first three topics they will decide. We talk about the instruction set architecture, and the fourth one, it gives how it is implemented, the micro instruction part. So that we are going to cover in this lecture series. So what are the basics of instruction set architecture? As we said, the basics means we are going to talk what is the structure of the instruction set architecture. So the general structure. So general structure of your operation of the instruction set, we say that the computer is having three different components. One is CPU, another one is the memory, and another one is input output devices. Three different components will be there. So these are connected that we observed in previous series. So in instruction set architecture, we mainly focus on the CPU and how the data is transferred from CPU to memory and memory to CPU, that we are going to talk. We are not going to cover about the input output, the instructions. So the basic structure of this instruction set architecture, it follows the definition, or it gives that the instruction set architecture is the structure of a computer that a machine language programmer must understand to write the program for that machine. So that is the architecture. So simply we say that instruction set architecture gives the details about the structure, how the instruction should looks like, and one programmer must write that the operations in that structure itself. So this concept in instruction set architecture, which was defined and following this, the IBM concept that is introduced by the IBM 360 machine in 1964. So what exactly is there in this instruction set architecture? So this ISA defines three major components in that. What is that? First, it have the operations that the processor can execute. One is operations. Second one is provide the data to the operations. So for that, the data transfer mechanisms will be there. And once you have the operations and data, by using operations and data, you are supposed to write the programs. So in that programs, you will have certain blocks. So we call them as control mechanisms. So that control mechanisms gives some conditional or unconditional blocks. We call them as branches or jumps. And finally, it defines as the ISA is a contract between the programmer who is writing on a compiler editor and the hardware part. That means what? As we discussed what is computer architecture, there we define that the computer architecture first phase is your ISA, which lies in between the software and your hardware. So hardware, that is using the VLSI technology or transistors. So this ISA instructions plays a role between the software and hardware. In software, they are written in high-level language, and your compilers will try to convert that. These compilers try to convert this high-level language into the machine understandable language. So now question here comes that what are the different operations that the processor can execute? So we observe that there are ALU machine is there, arithmetic and logic unit machine is there. So it performs the arithmetic operations such as your addition, subtraction, your division or multiplication. Whereas your logical operations that covers your AND operation, your OR operation, logical operations, or NOT operation, or exclusive OR operation. Along with that, there are some other commands are also there. That is, store the data and retrieve the data, and some functional operations will also be there. So let us consider from this arithmetic for the example, for this arithmetic operations like plus, minus, division, and your multiplication. Suppose we call these operations as binary operand operations, or binary arithmetic operations. Why we call every operation requires two operands to perform the operation. So it requires two, so we call binary, and we are doing the arithmetic operations, so binary arithmetic operations we call. Okay, so whatever the A and B that we are supplying to perform this operation, we call them as data. So this data will be stored somewhere in the memory, stores somewhere in the memory. So where you might have heard about the registers in computer organization course. So there are 24 registers are there. There are 24 registers. So out of 24 registers, 16 registers are we call the general purpose register. General purpose register, and 8 registers we call the special purpose registers. So these general purpose registers are named as the R0, R1, R2, and so up to R15. Whereas special purpose registers, you might have heard about the program counter, PC, instruction registers, your data register, your address register, and so on. These special purpose registers that you will mention. So in our programming language, we are following the assembly language code or instruction set, where we use the register. General purpose registers are used to store the data. Like A and B, they are going to store in the register memory, right? And when this operation is going to be performed or executed by your the processor, then these data can be retrieved from these registers, and operation will be performed, and that operation will go and store in some register. So that's why we call data transfer mechanism from register to the accumulator, the AC. That's also special purpose register, accumulator. And once the operation is performed, then the result go back and store in the registers. So then comes to the control mechanism. If you write any simple programming language, suppose if C programming you are taking, then we write that in the main program. You can write like add function, add addition of two numbers, your subtraction of two functions. Then you start writing about separate your add, the one, and you write some code, and then you write the subtraction, and the statements will be given. So what is happening here? Once this main function is executed, start executing it, enter into this line and say it finds this is a function, then control goes directly from here to here, and then this body of your add function will be executed and go back, the control go back to execute the next line in the main function, then control goes to execute this body. So that is, jumping is happening from one line to another line, and branches will be there in this program. That's why the control mechanism is updated in the instruction set architecture. So now let us see the standard, the fundamental requirements of instruction set architecture. The fundamental requirement is the ISA must be Turing complete. ISA must be complete means so that it can run any computer programs in a finite step. So all the instructions must be finite. At the same time, there should not be any ambiguity. Means try to reduce the dependability and finish the execution of the instructions in a given time. So that we call the Turing complete. We observed what is Turing machine in the previous lecture. So an architect, what is this Turing complete? That means this is an architecture is Turing complete means the architecture can simulate any Turing machine, and intuitively a Turing complete architecture can run any computer programs in a given time. That is the fundamental requirement of your ISA. So then come and talk about the standard structure of an instruction. This is very important. The standard structure of an instruction says the instruction typically has an operator, as said, the operations that the processor can execute. So that can be written sometimes by OP or opcode. And for that operation, as we discussed, the arithmetic operations are either binary arithmetic operation, and some operations are unary. So as we said, the arithmetic operations like plus, minus, division, and your multiplication, they all are binary because they requires two operands, a plus b, or a minus b, a divided by b, or a multiplied by b. So based on that, the operations, the instruction set has an operator, that is operations, that is OP. It can be written as OP and opcode, and one or two, or in this arithmetic we say two source operands, A and B. You write them as SRC, and one destination. The result will go and store somewhere. The result will go and store somewhere in the same the location or somewhere. So we call it as destination. That is destination operand. Right. So from here we are using the term, another one is one or two sources. So from this arithmetic operation, this subtraction symbol can be used. This can perform two different characteristics. One is binary arithmetic operation, as well as unary. Means sometimes we can write the numbers as minus A, minus B, minus C, like that. So it is having only one operand. So that's why we are saying that an instruction typically has an operator and one or two operands and the destination. So that is the structure of an instruction. That is the structure of an instruction. So in generally, it is written as the operation, then the source 1, and your source 2, and the destination. So this is a standard format, but the representation, because for its definition it requires one operator, and two operands and one destination. So the standard structure is written by following certain predefined rules. As we talked about the computer architecture, it is predefined rules and methods. So it is written as the standard structure. Remember, operation comes first, then the destination comes, then source 1 comes, then source 2 comes. So this is a standard structure of the instruction of a processor we call the Intel processor. Okay, so now here we use the terminologies destination, source, and source 1 and source 2. What it means, this destination, source, and source 1, they may be the register or they may be the DRAM. The operands may be in the registers, or the operands may be in the RAM, the non-volatile memory, the volatile memory, or the temporary memory we call. So that's why the terminologies we use, the destination, source, and your source 1 and source 2. And specifically, if it is mentioned that all the operands are in the register only, then instead of this one, it can be written, these operations can be written as the addition of two numbers, suppose C is equal to A plus B, can be written as the R1 is equal to your R2 plus R3. The operation, addition operation, can be written as the any programming language that is C is equal to A plus B, that will be written in the assembly language as R1 is equal to R2 plus R3, as said here. Here it is having the operator as well as the two operands. So here R2 becomes the source 1, R3 becomes source 2, R1 becomes destination. R1 becomes destination. So for these, how the instruction for this operation, how the instruction set representation will be there. So instruction set representation says which operation is here, addition. So the instruction, standard instruction, it follows the operation, then your destination, your source 1, your source 2. So operation here is addition, so we write it as your add. Destination is R1, so you write R1. Then source 1 is R2, so you write R2. And source 2 is R3, so you write this. So this is the instruction set for addition, or instruction for your addition operation. Addition operation. So from this, the slide, you can see this. In this instruction, R1 is equal to R2 plus R3. So R2 and R3 are two source operands as per the definition of this one, and it requires one destination. So destination is R1, and for this, which operation it is performing, the operator is plus, and the standard instruction is your add R1, R2, R3. That means add the content of your R2 with R3 and store the result in R1. So this is the standard structure of your instruction. Now here, let us see some examples. Suppose in the program somewhere we write the instructions that A is equal to some pointer variable, suppose P, in C language. So that can be written in assembly language as R1 is equal to the star of, it is following the address of the operator over there, right? So in this you are finding address. So the accumulate the C code for loading the value at the address add into the register, it writes the instruction as R1 is equal to star add. So here the source operand is address. The source operand is the address. The operator here using is the assignment operator. We call this as your load operation. Okay, load operation, and the destination operand will be there, that is R1. So if memory reference is there, then this kind of operations can be written in terms of instructions as it used for assignment operator. It use the instruction move. The operation code is move, and the destination is R1, and the operand is your address. So the address is always written in square brackets, and it is written the operator name. So this is the instruction for your memory. This is an example for your memory instruction, that is move the address into R1. Now let us see the another example. Now in that address, that some content will be stored into the address location. What it means? Let me define this. Suppose if you have a RAM memory, you are having a RAM, or the primary memory we can call, the RAM. In that primary memory, it is going to store some information. So it is identified with the addresses. It is identified with the addresses. So addresses, in a computer organization, you might have heard about this. The address represents like this: 002 for the first location, then 004 for the second location, 1008 for third location, and so on. So what it say in R1, some content is there in the register R1, some content is there. So the meaning of this one is your star your address is equal to R1, it says that at 1002 location assign R1 value. So that R1 value is you're at this location, you this store this 5 into this location. So this 5 goes and store in the RAM at the address your 5. So this kind of instructions are vice versa. Sometimes from the address will be stored into your R1. So that means it simply says in these instructions, there will be source operand is this one. The operator here is the load. So in that case, how you are going to write the instruction means the instruction is written as move the content R1 into the address, specified address location. So that is the instruction. And the writing this one star address is equal to R1 is the assembly language, right? So now come and see another example. So now we covered first one is arithmetic operations. First one is the arithmetic operations. Here how it looks like, the plus, minus, division, all those things comes. Then if the operand is in the memory, then how the instruction can be written, it is following the move address one. And as we said, your program can have the blocks. Your program can have the blocks. So what sometimes in the program you write that if A is greater than or equal to B, if A is greater than or equal to B. So in this case, you can write it as if the content, sorry, if A is greater than or equal to B, if such kind, here it is written as the if R1. R1 means your A is in the R1. If it is greater than or equal to the address, here B is representing the address of your some variable. In that case, it is a conditional one. If this is true, then only the block of if condition will be executed. This block will be executed. If this condition is fails, then this block will not be executed. The control goes to the else block. The else block will be executed. Correct? So in this, if such kind of, we call this as your logical instructions. Logical instructions. So for logical instructions, what is the instruction format or structure? So it is like this. It is given that the destination is implicitly in this logical instructions. So usually a flag register is used to represent this destination implicitly. So that is the zero flag. Zero flag. So here the destination in logical instructions use the special register we call the zero flag register. Okay, that zero flag register is used in the architecture. Your 8086, we are going to talk about this one later. But for here, for your reference, just remember this. So if the comparison result is false, if R1 is greater than or equal to address is false, then set this ZF register to be 0, sorry, to be 1, or else if it is true, then set it to the 0. So it goes and executing this instruction. So what it says, a C code for comparing the value at address with the value in the register. If it is true, then the Z flag register set to, if it is false, it is set to 1. If it is true, then your Z flag register is set to the 0. This is the implicit destination for the logical instructions. So if you find any of these kind of instructions in the program, if R1 greater than or equal to your address, then the instruction standard is written as, here we are comparing greater than or equal or less than or equal or greater than or less than. So these are comparison operations are going on. So the instruction used here is your compare. CMP is used comparing the operands, two operands, comparing two operands. One is your R1 operand. Another one is we are comparing in this instruction is address. So the address can be written in square bracket. So this is the instruction format of the logical instructions. Okay, I repeat, for the arithmetic operations using the instructions by following the add, subtraction, division, multiplication, and the destination, source, and your source 1 and source 2. If it is memory reference, we use the move. It is using the load operator only. If it is the logical instruction, then we use the comparison operations. The instruction use the CMP for comparison. So then comes to, as we discussed in the previous example, we say that if your A greater than B, if it is true, then this block will be executed. If not, if this is suppose false, suppose it go and execute the next block. So what is happening? All these lines, this line, and some block of code will be skipped and directly and executing from the next line. So that we call jump instructions. Jump instructions. So those jump instructions can be written, use that in go to the target. Go to the target. That means it says go to some 55. That means in the program, if it is having more than 55 lines, it says that go to 55 line. Go to 55th line. Or if it is written suppose 60, go to 60th line in the code. So in C code for unconditional jumps, means if there are no branches, for unconditional jumps to the code at the target, it goes to the target line. So it is written as there is one go to and the target. So it is having two source operands. Two source operands. One is the go to and the target. What it says, there is no destination operand involved here, but or you can view the destination as the program counter PC. So how this program counter works, that we talk in the execution implementation of these instructions. Okay, so that can be written as jump target. So here the instruction format which is used here is the standard is JMP. So that is jump instruction. Jump instructions. So now, if there is a conditions, as we said, if condition or do while condition, if else condition, for loops. So that is if else conditions, or do while conditions, or for loops. Okay. So if these kind of functionals are there, then the control mechanism comes. We call this jump instructions with the conditions. So what is happening? The conditions, the simple jump instruction, we write two operands, go to and target. Okay, go to the target, two operands, but it is having the what you call the conditions also. So in condition we said that there is a implicity register, that is ZF. The zero flag register is used. Zero flag register is used. That means what? If a condition A is greater than B, or in previous example we use that if R1 greater than or equal to the address. Okay, if this is false, then your ZF becomes 1. When it is 1, it goes to the target. If it is true, it becomes 0 and it will not execute this go to. So here the operator says that, first you need to combine this comparison operation. Okay, comparison operation can be combined with the CMP, and then the instruction to realize if then statements. So in a C code, for the conditionally jump to the code at the target if the zero flag register is not set. So for that the instructions written as JNZ, if this kind of instructions are there in high level language, then the instruction format or structure is given that JNZ means jump if not zero. Jump if the zero flag is not zero to the target line. So this is for conditional jumps. So now comes to, by taking these few standards, the structure of the instructions, the confusion instruction syntaxes come. So these syntaxes are very important. One should remember, if any programmer is going to write the instructions for certain the processor, they must follow the predefined rules and methods we call the instruction set architecture. So there are few processors are there: Intel processor, ATT processor, and some follows the technology MIPS technology, and ARM the processors are there. So what is the difference here? Let us see. So these syntaxes are very important to write the codes. First, the instruction set for your Intel 8086, or it can also be written sometimes as 86 as instruction set. So what standard it is following this Intel? It is following first the operation comes, operator comes, and after that the destination comes. After that, for the first source will becomes, the source one will come, then the source 2 will be come. So this is the standard structure. And we said the standard syntax for your Intel processor. So here we are using destination, source 1, source 2. As explained, this destination may be your register or the RAM. The same thing applies to the source and destination also. Then comes to another processor, that is ATT processor. For that, the instruction syntax is slight different. First it follows the operator or opcode, and then the source comes first. The first source one comes, then the second source comes, and once this operation is performed, it will go and store in the destination. Whereas in Intel, the destination comes first. In Intel, destination comes first, but in the ATT processor, destination comes last. So then the most of the processors, they are following the millions of instructions per second syntax for the MIPS instruction. So here you can see it mostly follows the Intel syntax, instruction syntax only. That is the operation, your destination, your source 1, and your source 2. Okay, but for some storage operations, once the performance is done, the storage operation we call the write back or store write back. So it follows the instruction that the storage instruction W and have only two operands, the source and the destination. Source and the destination. Okay, for storage purpose. For performing all the arithmetic logical operations, it follows the Intel instruction set syntax only, but for storage, it follows only this, the syntax where there are only two operands will be there, and that will use the command storage purpose. Now, so this is little bit confusion. For Intel, operation comes first, then destination, then source 1, source 2. For ATT, destination goes last. For MIPS, it follows the Intel syntax, but for storage purpose, it follows only this format: opcode, and then the storage one and source and destination. Then comes to the ARM processor. That ARM processor syntax instructions follows. This is very important. It gives the operation first, and here it is mentioned the register. Then your source or your destination will comes. So there are two operands will be there for this operator. So it is following only three separate items here. One is operation, another one is register, second one is source or destination. Second operand is from source or destination. So here you can see it is clearly mentioned in ARM processor. The instruction syntax clearly mentions that the first or the destination is always register. That means it will use only the registers R0 to your R15. No primary memory. RAM is not going to be used here. RAM is not going to be used as so specified here. But for your source and destination, it may be in your RAM, or it may be the source and destination may be in RAM or in registers. RAM or in registers. So that is the difference. So whether the second operand in this instruction set is source or destination, that depends on the operation, which operation it is following. But in our coming lecture series, I will use the syntax similar to the Intel syntax for 86 instructions. That means we always follow the operation, then destination, your source, and source 1 and your source 2 itself. So for the millions of instructions per second and the ARM, I will use their standard format for any special purpose. The examples are assignment. So now comes to the next part is key ISA decisions. Key ISA decisions. So you need to take the decisions based on how the instruction set is going to be designed and hardware. So these ISA decisions are taken on the operations, operands, and instruction format. Whether you are following Intel instructions syntax or ATT instruction syntax or ARM instruction syntax or MIPS instruction syntax, that depends. So what is this operations? So how many operations that you are using and which one is you are taking? So that gives whether arithmetic operations or logical operations or storage operations or control operations, that based on that the decision will be taken. And for those operations, how many operands you are going to be supplying, how many operands, whether you single operand or double operand or multiple operands. Okay, for unary operation like minus A, minus B, minus C, minus D, like that, single operands. If this subtraction becomes the binary, then we can write that C minus A, C minus B, or C minus D, two operands. And sometimes if you are going to follow the single instruction multiple data, in that case we simply apply where A is equal to 1, 2, 3, and suppose B is another operand which is having 4, 5, and 6, and suppose adding to giving the result that A plus B, then you can write it as 1 plus 4, 1 plus 5, 1 plus 6, or you can write 2 plus 4, 2 plus 5, 2 plus 6, or you can write 3 plus 4, or 3 plus 5, 3 plus 6. That means what? In everywhere the operation is same operation, single instruction, but you are supplying multiple data, 4, 5, 6, and 1 in one set. Then 2, 4, 5, 6 is another set. So that depends how many operands you are giving. Okay, and their location, the operands location, whether these operands are in register or in the memory in RAM. So in registers, if you are following the CPU memory, there you can find the cache memory also, cache memory, registers, and your RAM, where these operands are storing. Based on that, the ISA decision will be taken. Then type of operands, whether you are using the integer operands or the floating operands, the floating points, float values. Then how to specify these. And finally, the instruction format, how many bytes per instruction, whether it is 8 bits or 12 bits or 16 bits or 32 bits or your 64 bits. So how many bits of instruction format that you are following? We, in our exercises, in our entire course, we mainly follow the 8 bits and 12 bits for the the binary encoding instructions, encoding purpose. So then how many formats that you are using, how many different formats that you are using. So based on these three, the decision, ISA decision will be taken. So now let us see one by one. We come to the design choice later. First we try to classify. After classification, ISA classification, we come and talk about this ISA design. But in ISA design word, it is talks about the hardware part. So in the hardware part, ISA design it mainly focus on ALU, arithmetic and logic unit. So that is the hardware unit. Hardware unit. So this ALU unit, the ALU unit, this arithmetic and logic unit is a digital electronic circuit that performs arithmetic operations on source operands and produce the result. So in this, these registers, the source operands will be stored in the memory. Destination will also store in the memory. That's also in the hardware part. All the operations, it may be your arithmetic operation, logical operation, or your storage operations that will be controlled or performed by your ALU. So an ALU can be an arithmetic or bitwise logical operations, and the operands must be the integer values. Operands must be the integer values. So this is the design, a simple design part of your arithmetic logic. So based on this, we are going to talk about this design later. As we said, we talk about the ISA classification first. So in ISA classification is based on operands. Based on operands, as we are saying that these operands are in the cache memory, or in the registers, or in the RAM. So we simply say that we can divide this as whether they are in registers or the memory. Register or in the memory. So first one is based on operands, where the operands are. Okay. So let us see. This is the outlook of the typical the architecture of your Intel 4004 architecture. So here, what is you are having the operands are always going to store in the memory. So as we said, the memory maybe your registers or your RAM, cache memory or registers or the RAM memory. So in registers, again, you will have, as we clearly said, there are we use only the general purpose registers. General purpose registers. So in registers you can find the stack, or some special purpose register, whether it is going to be calculating or not. So the classification of your based on the operands, whether these operands comes from or maybe from your stack register, or from the accumulator register, or from the general purpose registers, or register and memory combination. One operand is in register and one operand is in the memory, as we saw in the previous example in previous slide. So what is happening, whether your operands are in the accumulator where the actual operation performs, or in some temporary registers, so that is the general purpose register, as we said, or they are in the stack one, or they are in some other part of the register. We call the register and memory, the RAM, we say. So let us talk one by one. If the operand is in the stack, then how the instruction format is. So based on the stack, the operands are read from the stack. The stack is inside the CPU, not in the memory, not in your RAM. It is inside the CPU only. Inside the CPU only. So in that, what operands to perform, as we said, ALU is arithmetic and logic unit. So suppose consider the arithmetic operations, like as we said, arithmetic operations are plus, minus, your division, your multiplication. In that case, these operations, the operators are in the ALU, plus, minus. So for this operator, it requires two operands. So both the operands if it is following the stack, both the operands are available in the stack itself. Stack is a registers. Okay, stack itself. In that stack, the first operand, first source, as well as the second source, both are in the stack itself. Those sources are given to your ALU. ALU performs this operation A plus B, and the result which is storing in the C, so that result go and store in the stack itself again. So that is one way. The operands are read from the stack, that is inside the CPU, and result will go and store in the stack itself. So as we know that, to perform these operations, stack is having two the operations. One is push operation, and pop operation. Push and pop. Okay, pop operation, when this ALU requires operands A and B are popped and supplied to your ALU. Once the operation is performed, that A and B, then the C will be pushed into your the stack. So further, to maintain which operands are on top of the stack, it follows the top of the stack pointer. So this is the first one, classifying ISA based on your stack. Okay, then comes to see the example here. The architecture with this implicity stack. Implicity means that is within the CPU only, not outside the CPU. Okay, within the CPU we may find the L0 cache, L1 cache, and L2 caches that we are going to cover in the upcoming lecture series. So that is inside only. So this stack acts as a source and or the destination. As we said, source means A and B both are in the stack only, source, and the C goes and store in the stack itself, that is the destination. So the top of the stack is the implicity that follows push and pop operations that have one explicit operand. So the example given, C is equal to A plus B, means first it push the first operand into the stack by following push A into the stack, and this operand, the TOS operand, is auto incremented top of the stack. Okay, that is auto incremented. Here it is mentioned square bracket. That means the address of the operand is of your stack. So that is the memory of A. The memory of A. Then you are going to pushing the B value in the stack. So that gives the memory of B memory. Then you are going to add this addition operation. So add. So that is the terminal. It will pop off this A and B. Okay. So stack minus, that is popping the operation. So your the terminal one in temporary register it stores. That means in R1 it stores the A, suppose B, suppose in terminal 1 top of the stack. Then in R2 it stores your A, and then it performs the operation in accumulator and store the result in C, that is pop the C, and push the result into the C. So this is the integer part, but in 8086 the floating points are also used this stack. That is complicated pipelining process. We'll try to discuss this later. So then comes to the second classification of ISA is your accumulator. So accumulator is a special purpose register. Accumulator is the special purpose register. So that special purpose register, it may be 8 bits special purpose register, or the 16 bits special purpose register. So in this, where these operands are storing, as we are saying, classifying ISA based on operands, where operands are stored in either stack or accumulator or register and your memory. Okay, so in accumulator the operands are read from memory. Which memory here? Mentioning memory means read from your RAM, and an accumulator. That means one operand to perform this ALU, one operand will be read from the accumulator special purpose register, and another operand read from the memory, and the operation will be performed, and the result will go and store in the accumulator itself. So first operand where C is equal to A plus B, in that case A is read from the accumulator. Second operand read from the memory, and result will go and store in the accumulator register itself. This is another part. Okay. In the previous case, there is a stack, all the operands in the stack, and result also in the stack itself, in the register, the special purpose register stack itself. But whereas here in special purpose register holds only one operand, another operand comes from the memory. So then it is written as the architecture with one implicity register, that is accumulator, that acts as a source and the destination, and another one other source is explicitly, that is in the memory. So as we see, first we load the accumulator value into the ALU. So load A from your accumulator. Okay. So then you add the B, which is from the memory. We said memory. That's why we are using the B is written as B is taken from the memory. So memory is written in the square brackets, and then store this value. Store the value in the the C register, C location, that is within the accumulator itself. So the accumulator is implicitly used and can become a performance bottleneck. So although in real CPUs, accumulators instructions are just conceptual, the actual implementation is register to register only. Register to register only. So in 8086 uses this accumulator conceptually for most integer operations, not floating point operations, right? So next comes to the classification of ISA based on your operands, that is register and memory. Register and memory. So in register and memory, the operands are read from the random accessible memory, that is your RAM, and the register file. In register file, the registers will be there in register file from R0 to your R15. So all these will be in the register file. So in register will be there. So one operand comes from the register, another operand comes from the memory and supplies it to your ALU. Then ALU performs this operation, and the result will go and store in the register. So that we call register memory. One operand from register, one operand from memory, and result will store in the register. Okay. So this another one is register to register or load and store. Register to register and load and store. So here what is there? If the operands are fed into the arithmetic and logic unit from the registers, so first operand, second operand for the operation addition fed from the registers, and but the value of the operands are explicitly read from the memory. That means what? They are following the values are in the memory, but first they take from here and store in the register. So how it will do? In register memory and register with the load and store, the most common approach is, it is very faster, temporary storages are used. The explicit operands are your register IDs, that we call the addresses. So for example, if C is equal to A plus B, in that case, how it is written in two different ways, in register to register instruction format and register to register with load and store instruction. You can simply observe here. In register to memory instruction format, first the address of operand A is stored in register R1. So loading here. Then the content of your R1 is added with the address of your B content and store the result in R3. So as we said, A is read from the memory, B also read from the memory. So whatever content is there, that content is loaded into R1, and that R1 is added with the content of your B. And then once this addition operation is performed, the result will go and store in the memory location of your C. Memory location of C. So that is register memory instruction. Another one is register with load or store instruction. So if you find register, you just realize here that first it load the first operand into the register, then second operand into the register. From the memory it is loading the memory value into register R1, then the second operand into R2, then it performs the addition operation, that is the content of R1 and R2 added and stored in R3, then that value will be stored into the memory. Okay, so this is the register to register with load or store instructions. So only difference is here the memory address is registered into the stores into the register and then operation performed, whereas register to memory, the memory address will be stored into the load into the register and then it directly perform addition operation and then store the result back. So that is the difference. Here you can find 3 instructions, here you can find the 4 instructions. So this 8086 ISA is mostly register memory. It is mostly register memory. So all RISC, the reduced instruction set computers, ISS, are the register to register with load and store. They follows these instructions. So for example, these RISC processors are ARM ISA is a RISC and the register to register processor, ARM processor. Okay, so with this, I would like to stop this session here. The classification of your instructions based on the operands where they are